this kind of work is somewhat motivated by the hiatus or lack of it. I think the one thing that you can say that's kind of come under the radar of the hiatus is that it's really stimulated the decadal variability community to understand more about what's going on. And I won't dwell on that figure. And it's really clear that something is going on in the Pacific, and I don't think that we have a complete handle on what that is. Just saying it's the PDO doesn't kind of really help us because we don't yet have a very well-developed kind of quantitative theory about how the PDO works. And as I'm going to show, I think we have some deficiencies in models in simulating this. So this is a poor reproduction of the figure from Matt's paper, fellow Matt, looking at this. You can at least see this black line, which is a kind of estimate of the strength of the trade winds in quite a sort of small region here in the Central Pacific. And this recent kind of strengthening of the trades, even though it's dipping down, it's a strengthening of the trades. Okay. I'm going to talk first a bit about not decadal variability, but sort of slightly longer time scale variability. This came about because we were looking in a study of atmosphere lapse rate and water vapor feedbacks in models and in satellite observations, and looking to compare historical simulations with observations and not kind of really understanding what's going on. And the reason for that is that if you compute this is the trend pattern, linear trend pattern, SSTs from HADIST from 1979 to 2014. So it's a 35-year period trend. And there's this clear, very large-scale cooling pattern in the East Pacific. And I guess kind of PDO-like. And if we look at the models, these are the mean of, I think about sort of 80-odd historical simulations joined up with RCP 4.5, because obviously the historical simulations stop in 2005. You don't see this pattern at all coming out. So a very simple way of quantifying this is to say, well, we'll have a box here, runs from about 10 south to 10 north in this East Pacific region, and a box here in this kind of warm pool Indian Ocean type region, and do one minus the other and plot a time series. So this tells us something about the east-west gradient. And if you do that, here is that index from 1979 up to 2014. The reason, of course, for looking at 1979 is this is the period where we start having quite good satellite observations of SST. So we're not relying on a huge amount of infilling of sparse ship records, et cetera, et cetera. And, well, of course, I mean, it's a trend, and it's going downwards, because it's east minus west. But clearly, there's a lot of interannual and decadal variability going on in this time series. I also plot here the PDO index this is the Mantua PDO index, and I missed off 2014, which shows a sort of red blob at the end, as Jerry showed earlier. And also the 10-meter zonal wind speed in the Nino 4 region, so a slightly bigger region than your region, Matt, but clearly showing this period of enhanced strengthened trade winds. So remember, because the wind's blowing east to west, the sign convention is negative. And you can see, you kind of stand back, you can see some good correlations between all these time series, as you might expect from the SST and the PDO, and also possibly this indication perhaps of some negative trend. So I don't have an answer as to whether this is really a trend or not, but I think it's useful to think about it in this way and work out the ramifications of what that would mean for all the work that we've done on forced climate change over this period. So if we take the null hypothesis that it is a trend pattern, and I'm willing to accept that it's not, but let's just assume for the purpose of this part of the talk that it is. And again, we look at the CMIT5 models. So this is a histogram of the trends from 1979 to 2014, historical and RCP simulations from about 80-odd CMIT5 simulations. So I've included all the models where we have multiple initial states. And these are 3 observational data sets. So the observations lie outside the range of the behavior of the models. So if this is an indication of some forced response in the system, then the models don't capture this at all. It's a serious discrepancy. If we look to our theories about how we expect SSTs to change, SST patterns to change under greenhouse gas forcing, there are a number of different ones. Possibly the most well accepted is the idea of having this peak of SST warming on the equator, kind of zonal mean picture, peak warming due to the weakened trends. And Shangping has a nice paper on this. There's a sort of ocean dynamical thermostat hypothesis, which I think is kind of less well accepted nowadays, but actually is the one which would fit the data best, with the east cooling with respect to the west, or at least not warming as fast as the west. And then the other hypotheses which are kind of derived from the behavior of the climate models, which show perhaps a slight tendency for the west to warm more than the east. I think these are theories of equatorial SST changes. They involve sort of upwelling and things like this. This pattern, if I can go back, this pattern is kind of broader than just an equatorial pattern. It has this subtropical component, and to me, it's kind of suggestive of some sort of fairly large-scale atmospheric process, but that's just kind of a hunch at this stage. So, some kind of intermediate questions at this stage. Are these really long-term trends that we're seeing in the Pacific, or is it just that we've had this recent kind of quite large amplitude negative PDO decadal event, which is kind of just skewing the, pushing the trend downwards in the latter part of the record? If it is a trend, do we need to revise our theories about how the Pacific will change? This is a trend over a 35-year period. 35 years from now, it will be 2050. That's a prediction, isn't it? And that 2050 is kind of in my mind as a point in time where we just don't need models anymore. We'll just have the signal from the observations. This is a fairly kind of long-term trend. Or is it just a decadal sampling issue? The real world did a big event. Perhaps the models don't capture it because we don't have enough realizations in the model world that we have, the sort of CMIT world. Or is really this decadal event that we've seen in the Pacific larger? Is it outside the range of what we're seeing in the models? So again, is it an indication of another model discrepancy? And of course, the other thing is, are we or have we entered a positive PDO phase? And this was just the SST anomalies on Saturday, showing this kind of fairly warm equatorial Pacific, at least. As well as getting calls about the hiatus, I get calls every week about, is there a big El Nino coming? And after last year, I'm saying nothing. And you'll notice that a lot of people are saying nothing. So just to go on to say something a bit more about long-term future changes, so thinking really here about the forced response and how robust that is. So we had a couple of papers. So the idea behind this paper is really thinking about, instead of defining El Nino in terms of the SST anomalies in the East Pacific, or in the Central Pacific even, for a Central Pacific event, that we redefine an El Nino event in terms of the precipitation response. And we identified these kind of extreme El Nino events where the precipitation, one of these lines is the precipitation, this is sort of composite ENSO events. In cases where the precipitation is shifted from the West Pacific right over into the East, kind of about as far as it can go, sort of almost pulling the ITCZ onto the equator. These extreme El Nino events, and if we look in the models where we see that those models which can produce these extreme events in the present day, how do they do in the future? Well, they get an increase in the frequency of these extreme El Nino events. There's also another paper which talks about extreme La Nina events, causing someone to ask me, when's the paper about extreme neutral conditions? That's coming. I'm sure Kai is working on it. So, how do we understand this? These figures are getting more and more washed out, but it doesn't matter. One of the crucial things is probably the mean changes rectifying the ENSO signal. So these take a bit of explaining. So this is a composite El Nino event from the ensemble of AMIP simulations from CMIP5, and it's the rainfall response. So it's showing, as we would expect for an El Nino event, increase in rainfall in the central and into the East Pacific for these more extreme events. So that's the kind of classical picture of a rainfall response to ENSO. This is the change in that pattern in what are called the future AMIP runs. So these are runs in which you rerun the atmosphere model, but you add on a patterned SST that is derived from the coupled models, and that is the pattern of SST. So you can see, although it doesn't come out as well as it does on the screen, that it has this kind of equatorial maximum with a slight shift, slightly greater warming in the east in comparison to the west. So here we're seeing this kind of extreme El Nino event. So we're pushing the rainfall response further into the east in these future AMIP runs, where we've got this pattern of SST. If you look at this just in the runs where there's a uniform SST pattern added, so there's something called the AMIP 4K runs, you don't really see much of a response. You see some response in the SPCZ, which I don't really understand, and this plot here is just the difference between this one and this one. So the signal of ENSO response and ENSO teleconnections in these experiments is really coming from the mean pattern of SST that we're predicting from the couple models and then putting into the ABIP simulations. And this, pattern is this sort of mean pattern of rainfall has this kind of, it looks a bit like an El Nino if you're looking in rainfall space, and it's kind of tied to this pattern of equatorial, sort of fairly robust pattern of equatorial warming in the models. So it's this mean pattern of SST change is feeding through onto ENSO teleconnections and these extreme events. So we're building up a lot of different links in the chain in order to support this idea of increasing future El Nino events. And I think the whole problem with both this and the sort of decadal variability aspect is that, in the Pacific, we've had long-term problems with coupled climate models. So this is something I pulled out of the IPCC report, chapter 9. What it shows is the black line is the observed pattern of absolute values of SSTs if you just concentrate in the Pacific region, and the red is the CMIP5 models with some shading, and the blue is the CMIT3 models, and they consistently show this cold bias in the models. Generally too cold. The trade winds are generally too strong. Possibly these two things are linked. There's a sort of equatorial dry bias in terms of the rainfall. The warm pool precip is kind of more fragmented. There's a sort of off-equatorial enhancement bias in the rainfall. And these kind of, I mean, you can see going from CMIT3 to CMIT5 got slightly better, but still things to do. And I think these biases, if we just go back one, this is based on Xiangpeng's paper. The contours, which I'm sure you can't see, are actually the climatological latent heat flux. So the climatological latent heat flux is a good predictor of the future pattern of SST change in the ensemble mean. Turns out it's not a good predictor of inter-ensemble variations. I'm not quite sure. There are probably other things going on. But this is potentially, this pattern of latent heat flux is potentially biased because of biases in the SSTs in the climate in the mean climate historical period. So there we go. There are discrepancies between the model and observed decadal to multi-decadal Pacific trends. Maybe it's just extreme decadal. So I'm introducing a new term here, an extreme PDO. Extreme decadal variability. I don't know. And I suppose I don't know that we could answer that question using the current set of models that we have, because a kind of way of doing that would be to do a sort of detection attribution type study. I've said the way, I think it's a way. And this wouldn't work. This would fail because basically there's no signal in the models world which looks like the observations. You at least need that as a basis for your detection attribution. These forced SST patterns also have a leading order impact on future mean rainfall changes, which I haven't really mentioned, around the Pacific Rim, extreme El Nino events, teleconnections, et cetera, et cetera. So my sort of open question, and I think we ought to bear it in mind for the discussions for the rest of the week, is, we can't just say, well, we'll just improve models and hope for the best, because it seems to be taking us a long time. We need to work out some way of making progress with the imperfect models that we have. So thank you.
Thanks. Questions? Go. Like you mentioned the tropical thermostat theory.
Yeah.
You said that was kind of less favoured, even though it seems to fit situations. So can you expand on why it's less favoured?
Well, it kind of relies on a constant upwelling of cold water from depth. And in the case where you have the trades weakening, that's going to reduce that upwelling from just Ekman dynamics. And the other thing is that eventually that cold water from depth, it has to come from somewhere, and it generally comes from off the equator in the subtropical cells. And if they're warming up, then that water warms up as well. So I'm not completely, it could be that is true, but there are certainly critiques of that particular theory. The authors aren't here, so that's a bit unfair. But if anyone is from that camp, yes, yeah.
Go, Ken.
Yeah, I was just going to make another comment regarding the biases. Another bias that we have in the models is the seasonal cycle of the SST in the equatorial Pacific.
Yeah.
A couple of models have the biannual signal as opposed to a single annual cycle. So I don't know whether it rectifies onto longer time scales or not, that bias.
Yeah, I mean, that's likely related to the position and the biases in ITCZ, I guess. So yeah, I mean, the other thing is, the Atlantic. Gosh.
The Atlantic is even worse, right?
Yeah, it's down here. Gone too far. Well, I mean, look, that's the observations from the Atlantic. These are the models. Anyway.
So I think Arun was next.
And when you compare the trend between observations and the models, as
assume that was based on individual runs of the models?
Yeah.
So the 22 individual runs from the model can replicate the observation.
Well, there's 80 because they have.
Okay, so 80,
Yeah.
so even worse. So that tells you something. Either
Yeah.
there's something missing in these models, that natural variability is not high enough.
I mean,
It's very hard to believe that it just happens that we are analyzing this period and observations tend to be just outside the envelope of the variability. That hypothesis is hard to justify.
Well, I think so. They're my statistical colleagues. You know, when I mentioned this to them, they said 100 models. That's nothing. You know. Well, okay, yeah, but you know, the whole of what we do tends to be based on the 5 percentile. You know, in which case that we can reject the null hypothesis that the models and the data are equivalent. I think in this case.
So for the hiatus from 2000 to 2013, there are 10 of 262 ensemble members that get the observed hiatus. So for a shorter time period.
So at least there are some.
There's some.
Yeah.
So, Matt, you said you related this thing to the bias, or you just mentioned the bias, but how does the bias explain why the models don't do it?
Well,
It should have made it easier for the models to create this cold Eastern Equatorial Pacific.
yeah, I don't know the answer. So my talk title was a bit more ambitious in terms of how far I would have got with this project idea. But yeah, I think it would be that would be a useful thing to be able to understand.
Paco?
Can you go to the last overheads? So the first sentence seems to give the impression that you expect to have some agreement somehow between the models and the observations. Am I getting it right or not?
Yeah.
Would you really? Because the CMIP 5 plot that you showed is an ensemble mean. It's a bit along the lines of what the group was.
Okay. We wouldn't expect the ensemble mean, I think, to look like the observations because there's lots of variability going on in the observations. But we might hope that the observations fall within the model simulations in the in the sense of a reliability diagram that you would use in seasonal decadal forecasting. I can't compute one of those because I probably don't have enough data points. But in that case, but the particular index I chose, which didn't actually take a lot of choosing, I didn't sort of tweak it, so it gave that result. It didn't really reproduce that. So
that one here goes out.
it's outside the range of So
Okay, that's what you.
yeah, it may be that we have to run 1,000 models, to get a 35-year period trend, and we sort of got into a bit of that in Chris Roberts' paper about so as you go to longer and longer hiatus periods, if you like, it's harder and harder to find examples, as you would expect just from statistics. You need so it could be that we just got unlucky, or it could be that there's something more insidious going on here.
Okay.
So another possibility that you're missing this, the observed trend for 35-year period, maybe the model's time scale, natural variability is shorter or different from observation. I wonder if you looked at the time scale. I mean, it's not really period in the model versus observation.
So I suppose, do we understand what would set the period for this type of behavior?
Yeah, I mean, maybe there is no set period, but at least you can say model bias toward differs from this particular observed period. I mean, not necessarily weaker amplitude is what I mean.
Yeah. Okay. That would be a good hypothesis to test.
Any other questions? Yeah, no.
I mean, with that distribution, it could just be that the distribution is the external forcing the model is too strong, right? The distribution should be shifted down.
Yes, I specifically chose the RCP 4.5. But if you look, don't have the picture. If you look at the global mean response, kind of all, it's not too bad. I suppose that's Ed Hawkins' plot from chapter 11. I'm thinking about the long. Yeah. Okay, we'd have to check that. Yeah. Okay, I'll check it.
You can just look at the natural, the 1850 forcing run and see if you ever get that much of a trend in any 35-year segment.
I haven't looked at
There's a lot
Yeah, or we just look in the control runs or something like that. Yeah.
You have a question? So George, before you ask your question, Alicia, why don't you come on up and start with the transition?
There were just 2 brief ones. One was the one that started off this discussion. How much do you trust the data? I mean, you seem to have 3 data points there, 3 data estimates.
Yeah.
Of course,
Yeah.
a long 35-year trend, where you start, when you end.
Yeah. I totally accept that, you could be selective in terms of your period. But it is the period where we allegedly have the best observations, right? We have satellites. This is 97 Yeah.
And then the last question, of course, was how do we make progress? You must have some ideas, right?
Well, I quite like the pacemaker experiment idea, but I think we need to think very carefully if it's the paper, the Kusaka and G paper. It's clear that if you're nudging towards SSTs, then you're not conserving heat. And then going on to look at global temperatures, I think we have to think quite hard about that. So there's an alternative approach, which is to nudge the winds, which but it'd be good to have some discussion about that.